Welcome everybody. Today I am going to present our research paper, Development of Spider Identification App, Spider ID App, using YOLO-based deep learning models. My name is Vincent Luong, PhD candidate of Department of Chemical Engineering, Institute of Chemical Engineering and Biotechnology, I-Shou University. I'm supervised by Professor Hong of I-Shou University and Professor Xiao of Chung-Der Christian University. Our app will be provided at our GitHub repository at the link below. First, let's dive into the background of our study, exploring the challenges and importance of spider identification. Up until July 2022, more than 50,000 spider species has been recorded worldwide by taxonomists. However, the identification is not an easy task, especially for non-experts, due to subtle differences and nuances. The requirement for computer vision aid tools, such as deep learning models, is the must. There were two studies that have pioneered in such approach. The first one was poisonous spider recognition through deep learning by Zinot et al. In 2020. In this study, the dataset is consisted of 9 common name spider groups, in which Australian tarantula spiders and Australian redback spiders are considered the venomous ones, hence the requirement to identify the venomous spiders. The dataset after undergoing augmentation of random cropping, resizing, and rotation was used for training in 3 different models: exception, MobileNet, and MobileNet v2. The optimization step was conducted based on 4 configurations: learning rate, batch size, dropout, and optimizer algorithms such as ADAM or SGD. The final F1 score of each common name group is quite high, with overall score reached 81% above. Such study has displayed a high performance in identifying spider. However, the taxonomic distance between selected spider groups within dataset were high. 9 classification classes belong to 9 different families and within 2 different infraorders. The second study regarding research on spider recognition from images based on deep learning by Chen et al. In 2021. In this study, they have collected data from 30 species from genus Pseudopoda with a total of more than 3,000 images. The dataset is pre-processed and augmented using 5 different methods, as listed on the screen: of flipping, rotation, zoom, contrast, and crop. 2 DNN models were tested, which were ResNet 152 and exception, in which exception was chosen for optimization steps. The final model reached accuracy on validation set at 98% and on test set at 92.38%. Such study has displayed a high performance in identifying spiders. However, the scope is limited in one genus. We anticipate that our research will lead to an application that can accurately identify spiders to the genus level, with a range of identifiable genera of 120. And with an application provided, an offline high-throughput identification can be conducted, regardless of the input or single image, multiple images, or a video. Our experimental design includes a pipeline study as shown on the screen. At first, we collect spider images from online databases, and then we create a spider dataset with annotation by using our own labeling script. The labeled datasets are split into train and test, and subsequently the trained ones are split into training and then validation. The datasets are used for training and retraining the models. 4 models were selected: YOLO v5, 6, 7, and 8 as base model of our fine-tuning process. Subsequently, the feature recognition are tested on the test dataset, as shown in the figure D. In detail, data collection and preprocessing are described on the screen. Our online databases used was iNaturalist and Taiwan Biodiversity Network. A total of 20,000 images was collected. After cleaning and quality check, we received almost approximately 24,000 images. These images are split into training and validation dataset and test dataset. The train val dataset was split with a Howell ratio of 80-20. All datasets are duplicated and relabeled for to make two separate datasets, which are with gender 1 and the no gender 1. Datasets prior being used into fine-tuning models must be augmented. In this study, we used three different methods for augmentation. This augmentation process are aimed to balance the dataset between the 120 classes for NG dataset or 240 classes in WG dataset. The vertical flip of 50% and rotate from 0 to 90 degrees, shear from 0 to 45 degrees on both X and Y axis were used as augmentation methods. Of course, the model fine-tuning of YOLO v5 to v8 all include their self-refined augmentation. However, these augmentation as default don't have vertical flip, rotate, and shear, and that's why we use these three methods for balancing first. The fine-tuned models are then tested on the test dataset. The hyperparameters optimization was conducted on NBS and resolution, which means the batch size and the image size. Due to the limitation of our GPU memory, which was only 8 GB, we cannot use the batch size of more than 8 for YOLO v7 or not more than 16 for other YOLO's version. That's why for testing and optimizing the batch size, we need to use nominal batch size, which is a hidden parameters in all four YOLO versions. The detailed explanation of NBS are inside the paper. Mode of evaluation metrics in this study include training progress metrics and final performance metrics. The training one are often coupled with time or epochs like loss values or MAP and mostly evaluated on validation set. This one aims for tracking and guide the parameters tuning in during the training process. The final performance metrics, on the other hand, such as F1 score, accuracy, etc., are usually measured at the end of the training process, and they are evaluated on the test dataset, which are separated and not used during training. We also introduced a new model evaluation matrix, which is Spider Identification Scoring System, SISS, to accommodate for the need of comparing between our models, which are identifier with confidence value, but can only provide the result to genus level, to the identifier without confidence values, but can display the level, taxonomy level at different ranking from species to genus to subfamily to family, etc. In this study, four YOLO-based models, YOLO 5, 6, 7, and 8, was selected and then trained on both datasets, WG and NG. Result is the two graphs we can see on the screen. In both graphs, based on the MAP 0.5 to 0.95, the performance of YOLO v7 is considered the best. In the evaluation of the four models on both datasets using area under curve of ROC, it can be observed that the YOLO-V7 models are among the top performance, and selecting a pair of models from the same base model facilitates the development of the final application. Hence the YOLO-V7 model pair being selected for the optimization steps. In the first optimization step for YOLO-V7 models, the resolution selected were 416, 512, and 640, in which 416 and 640 are the default image size of several YOLO models. 512 was selected due to the majority of input images that we collected from online database has the maximum size of 512. Evidently, when tested using the classification loss values as evaluation value, we see the resizing resolution of 512 results in the best performance. Similarly, when evaluated using F1 score and SISS, 512 proved that it is the best performance configuration for image size. The second optimization was conducted on the batch size. 4 different configurations of NBS was used: 16, 32, 64, and 128. On the right side, we can see of the heat map the difference between the configuration. The redder the cell were, the lower the values respecting to the others. Nominal batch size of 64 have the best performance when evaluated by classification loss throughout the fine-tuning process. After optimization, all models are retrained, and a final cross-model evaluation was conducted. YOLO-V7, WG, and NG perform better than other model pairs. To prepare the best for our application to be utilized in the real-life situation, we test its flexibility and robustness. For flexibility, we test the models across different image sizes. A slight decrease in performance was observed when tested on different images resolution other than 512, a resolution that we used for training. This small decrease normally don't affect much. However, it can also be easily resolved by auto-resizing image before inputting into the model. For robustness assessment, we created an augmented test dataset by using several augmentation methods. Not only 3 methods used for trained VAR dataset, but also built-in augmentation of YOLO. With the aim of mimicking the real-life images occlusions, we then evaluate the performance of models using SISS and calculate the change between models tested on original TED and augmented TED. The non-balanced versions are the models use optimized parameters but not the augmented training dataset for fine-tuning. We can predict that the final version of the model YOLO-V7, WG, or NG will have the better robustness. But let's see. In the non-balanced version, the decrease between TED and TED augmented are 8%. But for the final version of WG, it's only 3.8. A similar phenomenon can be observed in the NG version, which means that the final version of YOLO-V7's WG or NG have a better robustness. Interestingly, in the YOLO-V7 WG, the final model exchanged a small performance decrease toward the optimal test set, for a higher increase toward a much more alien test set, which means an overall increase in performance toward any images being input into the model in the later stage in real life. For YOLO V7NG, the final model is better overall comparing to the non-balanced one. Eventually, we compare our models to iNaturalist identification tool. Given iNaturalist's expansive and diverse metadata, it was necessary to create an evaluation set composed of only locally stored images, annotated by Spider Express to establish reliable ground truth values. The evaluation set consisted of 51 images, gave us 59 points, and gave iNaturalist 57. It was a small margin win for us. Within 51 images, there were 11 images that contain spider genera not included in our training dataset, which means we score 0 and iNaturalist scores 4, a loss in this set. However, when considering the potential point, in the total we score 59 over 102, and iNaturalist score 57 over 102. But in this subset of 11 images, we score 0 over 0 because if the genera is not included, the potential point is 0. However, for iNaturalist, the potential point is 22, but they score only 4. The models, after tested, are then packaged into an application called Spider ID app. The highlight of our application is the easy-to-use setup and run. A user that is not coding familiar can download the whole project from the repository and then run the setup for installation and then the run file. The application manual is quite simple. You can follow the natural order from top to bottom of the buttons to access all the features. In conclusion, a YOLO-based deep learning model for spider genus recognition was created on the base of YOLO v7. It demonstrates competitive results regarding iNaturalist identification tool. Spider ID app, a Python program featuring a user-friendly GUI which includes YOLO detection properties with added enhancement for user convenience and improved analysis, featuring single and multiple images identification with detailed and summarized results respectively. Video and stream also supported, and with added features of pause, stop, display, and export results. The developed software offers versatility, robustness, making it accessible for all users, including non-scientists, contributing to advancement in spider taxonomy classification. Thank you for listening, and please follow up to our paper publication for more detail. Thank you again.